Hello, Geography 212 class. This is week 13 in chapter 12, calling it tropical weather. Essentially, what we're going to be looking at here are going to be tropical cyclones. So let's go ahead and get started here. All right. Now, we'll get into some terminology in a bit here. You probably know tropical cyclones in North America as hurricanes, and that's indeed what we call them. So let's just start with that designation here. You can see this definition here. The really essential characteristic for being a hurricane is recording a wind speed at a minimum of 74 miles per hour. Once it reaches that speed, it is designated as a hurricane. Now, we call these tropical cyclones as opposed to extratropical cyclones. You can see in the second bullet there. We've talked about extratropical cyclones. Now, what are some of the contrasts? Well, number one, there are no associated fronts. There's no warm front, no cold front, no stationary fronts. So that really sets them aside. Second bullet down is that sea level pressure is generally greater, or sea level pressure is generally less, and the horizontal air pressure gradient is typically greater. Okay, so the greater the pressure gradient, the greater the wind speed, and that's one of the reasons why tropical cyclones tend to have greater wind speeds than extratropical cyclones. It's due to a much more intense air pressure gradient. Hurricanes tend to be smaller systems. They're not necessarily. On average, they would be. There's been some very large ones in the past, but for the most part, they tend to be smaller in diameter than an extratropical cyclone. And the last bullet down is a real big difference. Mature hurricanes are what we call warm core lows. Now, their circulation is also counterclockwise, but the circulation weakens with altitude, which is opposed to an extratropical cyclone whose circulation strengthens with altitude. Okay, some of the characteristics. We have an eye. Okay, these tend to be cloudless. And a real difference here between an extratropical cyclone is that the wind is descending in the eye. Now recall, in an extratropical cyclone where convergence occurs at the surface, you're getting ascending air. So it's really almost a totally different system, all right? Okay, you can see what the diameter is there. Eye tends to shrink as a hurricane intensifies, okay? So in terms of the eye wall, which is bordering the eye here, this is where the strongest winds occur. They're cumulonimbus clouds and produce very strong winds and rain. Now we're talking about the most dangerous and potentially most destructive part of the hurricane. Okay, this is going to be imagine, if you can, a hurricane moving up the east coast of the United States, and picture counterclockwise circulation. Okay, that's going to put onshore winds to the north of the center of the hurricane. And onshore winds are going to produce the strongest storm surge. That is the most dangerous side of the hurricane. We'll take a look at some paths here in a few minutes. Let's just take a look at we'll come back to this in a sec. Let's take a look at a real schematic, a real general diagram of what a hurricane looks like. You can see in the center, we have air that's descending. You see the counterclockwise circulation at the surface and near the surface. And I'll go to one more here. This is an actual satellite image of Hurricane Elena back in 1985. You can get an idea here. Well, first of all, the counterclockwise circulation, the eye here in the center. But you see these bands of intermittent, relatively clear air, and then bands of cumulonimbus clouds. And that's the structure of the hurricane. We'll go back to this one. One of the other things that's kind of interesting with hurricane is that yes, the circulation is counterclockwise. However, by the time we get to the top, we get this clockwise circulation that spreads clouds out in a clockwise manner. And here is a cross-section of a hurricane to also give you some idea of what this looks like. Here we have the descending air in the center. And remember, why is the eye clear? Remember that descending air compresses, warms, and dries out the air, so it's going to be clear, relatively free of clouds. And then we have these alternating bands of cumulonimbus clouds, descending air, compressing and warming and drying the air, so it's relatively clear there, and on we go. So this would be a cross-section of the eye of a hurricane, or rather of the entire hurricane. All right, so what are these necessary conditions and where do they form? Well, first of all, you need a high sea surface temperature. And The limit we use is around 80 degrees Fahrenheit, and it has to be a relatively deep depth of about 150 feet. So in other words, we need a pretty good supply of very warm, moist air that we're going to get off a sea surface temperature like that. All right. Once we get evaporation of warm surface air and it condenses now, we're going to get a tremendous amount of latent heat release. Remember that when water vapor converts to liquid water, which with these clouds are liquid water, it's going to release tremendous amounts of latent heat, and that's going to continue the development. So a lot of the development occurs from latent heat. Sea surface temperatures, in terms of when the season's going to be, when we have the right sea surface temperature, most Atlantic hurricanes develop in the late summer into early autumn. Late summer because it takes a while for the sea surface temperature to reach these relatively high temperatures. So it's going to be later on in the summer. Now, this is only talking about Atlantic hurricanes. Keep in mind, we have Pacific hurricanes. These are going to form up off of Baja California and Central America. And these Pacific hurricanes are the ones that can affect us here in the Southwest. And we do get fairly frequent weather from these systems. Okay, we need to have adequate Coriolis effect. Recall that as we right at the equator, we get none. And then as we proceed further north, we get more and more. So we need to get a little spin from that Coriolis effect. So generally, these tropical cyclones are not going to occur within 5 degrees of the equator. We also really need to have weak vertical wind shear so that we can allow clusters of cumulonimbus clouds to form. In other words, we need to have instability so these cumulonimbus clouds can develop to a high elevation. If we have strong wind shear, it's going to tend to blow them off, and they're not going to get that vertical development we need. Okay. Now, as I said, we call tropical cyclones hurricanes in the Americas. So if we start here with the Atlantic, you can see this whole area starting from just off the coast of West Africa into the Caribbean. We can even see hurricanes develop in the Gulf of Mexico. Anyhow, this is the general path that they're going to follow. You can see as they curve back, this is because if they drift far enough north, and usually they do, they're going to get caught up in the westerlies and get blown back to Europe. Okay, here's the source area for Pacific hurricanes, Baja, Mexico, down into Central America. These generally move out into the Pacific on the easterly winds, but can occasionally get blown back by the westerlies and affect places like Arizona, and they do. If we get tropical cyclones forming up in the mid-Pacific out here into the western Pacific, they're referred to as typhoons. Okay, but it's the same kind of system. All of these things, the better name for them are tropical cyclones. We simply call them different names in different locations. If you see a tropical cyclone form up south of the equator, they're referred to as cyclones, to further confuse the issue. And to make that even more confusing, if we have a tropical cyclone develop north of the equator over here, that would actually be the Arabian Sea, that area, and also over here just south of India. They're called cyclones. Okay, now here are the frequency of Atlantic hurricanes and tropical storms. Okay, so if you look at the peak here, you're going to see it's right around mid-September. So that's peak season, but it definitely carries on into into October, into November, and occasionally even into December. Okay, so we can see a start season as early as May, but generally doesn't get up and going until August and September. Okay. All right, now go through the life cycle of a hurricane. I'm first going to start off as something called a tropical disturbance. All right, and let's take a look at this. Tropical disturbance, you can see it right down in here. It's basically a cluster of clouds, no real organized circulation, no strong wind speeds at all. But if you see a cluster of clouds like that in a tropical area, we'll keep our eye on it. It's an area of interest, and because that might develop into a hurricane. Okay, the next step progression that we go on to, if this tropical disturbance gets organized and starts developing a wind speed of 23 miles per hour or higher, we now call it a tropical depression. So we look at our satellite image here. You can see this is much better organized than a tropical disturbance. We're getting some counterclockwise circulation here. Okay, the next step up, tropical storm. Okay, tropical storm is when we reach a wind speed of at least 39 miles per hour. Now, at this stage of the game, it receives a name. It's now called a named storm. But you got to reach 39 miles an hour to get it. Once you get a name, you keep it. All right? And here, let's take a look. Take a look at, here's a tropical storm. That was Amelia. That's what that would look like on the satellite. And then finally, in the fourth stage here, if you reach a wind speed of at least 74 miles an hour, you now assign the name of the hurricane. All right. Now, as the storm weakens, and they will, it's downgraded by simply reversing this classification process. So you can work your way up from a tropical disturbance to a hurricane, and you can work your way back down through that cycle. And there would be a hurricane, you can see on satellite image. All right, so as I said, the hurricanes that affect North America are going to be Atlantic hurricanes that form up the coast of West Africa, and then into the Caribbean Sea and Gulf of Mexico. And then, as I said earlier, Pacific hurricanes form up the west coast of Central America and Mexico, and they can affect us and occasionally the west coast of North America. Now, where do these things form? Why do they form? You're going to get an organized cluster of cumulonimbus clouds, okay? You need to get a ripple or a wave, okay? In this case, it looks like a ridge, okay, that's going to form out over this area. And this is what we look for in the development. In other words, if we see this kind of thing forming out there, we could think that perhaps a hurricane's going to develop. Let's go to this site. Let's show you something here. All right, you can see that in terms of Atlantic hurricanes, we have a set of names already established over the next several years. And so our year right now, 2016, you can see that we're up to a Nicole right now in terms of Atlantic systems. And anyway, those will be the next names that develop, or if these hurricanes develop, that's what they're going to get. So you can see these names are already established up to the year 2021. So the Pacific hurricane names, the ones that can affect the Southwest, we can see over here. We're down to Seymour this so far in the hurricane season in 2016. So you can see what the next ones are going to be. All right. Now, we do retire names. Let me show you this list. In other words, if we get a hurricane of especially devastating strength, it's called, devastating strength, we're going to retire it and never use that name again. So here are a list of the retired Atlantic hurricane names. And one year of particular interest to a lot of people was the year 2005, right here. This is the year we retired 5 hurricane names. Now, most people will remember 2005 from Hurricane Katrina. Yes, certainly a devastating storm. But a lot of people forget that Hurricane Rita hit almost the exact same location a couple of weeks after Katrina. And it was a powerful Category 4 hurricane when it hit the coast. So we retired that name as well. All right. One other fact about the year 2005, you saw earlier the list of names that we have. We had so many hurricanes in 2005, or Atlantic hurricanes, that we ran out of names. And in fact, we had 3 other hurricanes that developed that we had no names for because we retired the list. And so what we did, we called them hurricanes Alpha, Beta, and Gamma, and that's never happened before. So the year 2005 was the busiest of any Atlantic hurricane season. All right, you can see that these can take some very interesting and unpredictable paths. So let's go down to the next slide here, and you can see a little more detail here. I just put a few on here you can take a look at. Take Hurricane Elena here in 1985, for example, as it heads toward New Orleans, and then turned away, and with a lot of relief to people living in Louisiana. But then look at this. Did a loop, came back and hit it. Now, why would it do that? Well, it turns out surface features, particularly high pressure systems, can block the path of these tropical cyclones, and that's indeed what happened here. It also happened for Hurricane Gordon in 1994. Hurricane Gordon was heading out across the Atlantic. A blocking high in this area sent it right back in toward Florida. So anyway, a lot of these what look like erratic paths can be explained by surface features that divert them, all right? Now, we've been sending aircraft into hurricanes to penetrate the eyes for decades in the United States. And you can see over here on the right, one of the first aircraft we sent through are Lockheed Constellations. Today, we send both of these types of aircraft in, the Lockheed P-3 Orion and the Lockheed C-130 Hercules. Both types will continue today to fly into hurricanes. Now, I've put a couple links for you to look at. You go ahead and take a look at them on your own time. I particularly recommend the first one here on the top. That's going to be a Lockheed P-3 Orion penetrating a particular hurricane. It might seem crazy. I'm an aviator. It might seem crazy to fly into a hurricane, and it is. And you need a pretty robust aircraft to do it. And I think that's a testimony to the type of aircraft that Lockheed builds. As you can see, all of these hurricane hunters, as we call them, are Lockheed aircraft. I think what we're going to find in the not too distant future, we're probably going to discontinue sending aircraft with humans aboard into these hurricanes. We're going to probably substitute them for drones. All right, we're already using drones to a certain extent to investigate hurricanes. All right, so why do we want to send aircraft into the eye of a hurricane? Well, we can't get a really accurate barometric pressure reading unless we do that. So that's one thing we can get. We can get a really good determination of whether the eye wall is building or receding to determine if the hurricane is strengthening or not. And we get to pinpoint its location. All of this information from these aircraft are radioed back to the National Hurricane Center in Miami, and it allows the National Hurricane Center in Miami to be able to plot and forecast the direction of a hurricane. So these aircraft are providing essential information for us. They have for a long time. All right, so what are some of the hazards associated with hurricanes? Well, number one, and this is something you may not have suspected or may not have thought was the primary hazard, is inland flooding from heavy rain. It's not storm surge, it's not high winds. It's once these tropical storms come over land, yeah, sure, their winds diminish, but their rains do not. And so we can get tremendous flooding from hurricanes, all right? So if you take a look at this stat I put here in the first bullet, you'll see that flooding was responsible for 60% of the deaths between 1970 and 1999. Okay, number two, yes, strong winds are certainly responsible for deaths, but this is going to be out along the coast, okay? Tornadoes can be spawned. Remember, these are cumulonimbus clouds. Tornadoes are spawned from cumulonimbus clouds, so we can get tornadoes developing as these hurricanes come ashore. Storm surge, okay, well, all a storm surge is a high tide moving inland, particularly because an onshore strong wind from a hurricane can push this Pacific, or rather push the ocean far inland. Just to give you an example, a few years ago, when Hurricane Sandy came ashore in New York City, it created the highest tide ever recorded in the New York harbor, okay? So storm surges can cause drowning fatalities along the coast. All right, how do we identify the intensity of a hurricane? It's called the Saffir-Simpson Hurricane Intensity Scale. It's based solely on wind speed, all right? So in other words, a Category 1, that's your minimal wind speed to develop a hurricane. Here you go, 74 to 95 miles an hour. These storm surges are simply going to be estimates. It can vary. There's other factors other than the wind that can affect the height of the storm surge. Category 2, you reach 96 miles an hour. Category 3, you reach 111. Category 4, you got to reach 131. And finally, the highest category of a hurricane, you're going to have wind speeds of greater than 155 miles per hour. Okay? Now here's a table of what we call the 10 deadliest hurricanes in the United States from 1900 to 2008. And still, nothing compares to the Galveston hurricane back in 1900. If you're not familiar with Galveston, it sits on Galveston Island. It's very low level, not far above sea level at all. The forecast was was mishandled, let's put it that way, back in 1900. You know, it's easy to second guess these guys, and we had no satellite support and that kind of thing. So this one got mishandled, and people didn't get enough warning for this one. Anyway, you see the deaths is 8,000 plus. I've read estimates over 10,000. And so this hurricane still remains the greatest deaths from any kind of natural hazard ever in the United States. Anyway, the list goes down. The one that a lot of us are familiar with, 2005 Hurricane Katrina, which killed approximately 1,500 people. Anyway, you can just take a look at that list. Okay, trends in hurricane frequency. Now, this is an interesting thought here. In other words, you know, there's a, and we'll get to this later at the end of the course, you know, this idea of climate change. Is the climate changing? Is it getting warmer? If it is getting warmer, would that create more hurricanes? Would they become more intense and all that kind of thing? And so here, I'll give you some data here in this chart from 1970 up to about the year 2004. And we take a look at, you know, the number of hurricanes by category, okay? So you can see in terms of category 1, this blue line, category 1 seemed to have actually diminished over time. If we take a look at category 2 and 3, the green line, it's kind of been variable, maybe slightly diminishing recently. But here's the important one. Look at this. We take a look at category 4 and 5, the devastating hurricanes. They have definitely increased in number since 1970. Now, is this a fluke? What is this statistically significant? I'll leave it at that right now. This is just some data we've got. The other literature that I've read suggests that it does seem like we're not seeing a number, you know, the frequency of the hurricanes increase, but it does seem like we might be seeing greater intensity hurricanes. That's not been really verified yet, but that seems to be what the literature is suggesting. So that we're not seeing more hurricanes, but we're seeing more intense hurricanes. And again, there's another way to look at this data. Number of hurricanes and number of named storms. You can just have a look at that. Okay, hurricane modification. Is there a way we can go out and do something to these hurricanes as they come in off of the coast and perhaps weaken them before they hit the coast? Well, you can see the second dash down, this working hypothesis, that if we seed hurricanes with silver iodide, could we possibly, reduce the wind strength? Really, the jury's out on this, and we have had very limited to no success in doing this. And you can see Project Storm Fury. We've curtailed the program. That's not to say we might attempt something like this in the future, but for now, it doesn't really seem like we have a way of being able to do this. Okay, and that's the end of this for now, and we'll talk to you later.